All right, let's dive into the world of automated theorem proving. It's a field where things are getting seriously shaken up thanks to machine learning.
Hmm.
We're looking at this research paper, Efficient Neural Clause Selection Reinforcement. And trust me, it's way more exciting than it sounds.
You're right. It's pretty groundbreaking stuff. We're talking about using computers to tackle one of the most fundamental challenges in mathematics, proving theorems.
Yeah, it always seemed like one of those things that only, super genius mathematicians could even attempt. So where do computers even begin with something like that?
Well, this paper focuses on something called saturation-based theorem proving. It's a specific approach where you essentially try to build a logical argument to show that a statement can't possibly be true. Imagine trying to build a tower out of blocks, but proving that no matter how you arrange them, the tower will always collapse.
Okay, I'm kind of getting the logic puzzle analogy here, but I'm guessing it gets a lot more complicated than just playing with blocks.
Oh, absolutely. The real challenge lies in something called clause selection. In this Tower of Logic analogy, think of each block as a clause, which is a piece of the logical statement. And the problem is, there can be a massive number of these clauses to choose from.
So it's like trying to find the right pieces of a giant jigsaw puzzle, except this puzzle is made of logic statements. Sounds daunting.
It is. And the traditional way of tackling this has been to use simple heuristics. Things like picking older clauses or clauses with fewer symbols. But these methods are pretty limited.
So that's where this research comes in. They found a better way to guide the computer towards the right clauses.
Exactly. What's really exciting is that they're using a neural network, a powerful type of machine learning algorithm to do this. It's like giving the computer the ability to learn from experience and make smarter decisions.
Okay, I'm intrigued. But before we get into the nitty-gritty of how it works, can you back up a little? What's the given clause algorithm and how does it fit into all of this?
Sure. The given clause algorithm is essentially the set of rules that guides the theorem prover as it tries to build its tower of logic. It tells the prover how to choose the next clause to work with based on the current state of the proof. The problem is, this algorithm relies heavily on efficient clause selection, which is where things get tricky.
Right, because finding the perfect clause would be like knowing the answer to the puzzle beforehand. So how does this neural network actually help?
Well, instead of relying on predefined rules, the neural network learns to identify promising clauses based on past experience. It's like watching an expert solve a puzzle and trying to pick up on their strategies.
So they're essentially training a computer to become a master puzzle solver. That's pretty wild.
It is, and they've designed this network in a very clever way, combining two powerful types of neural networks: graph neural networks, GNNs, and recursive neural networks, RNNs.
Whoa, those are some serious acronyms. Can you unpack those for us? What do these networks actually do?
Think of it this way. The GNN is like the network's first impression of the problem. It looks at the overall structure of the logical statements, analyzes the relationships between different symbols and clauses, and creates a sort of map of the problem space.
Okay, so it's getting the lay of the land. What about these RNNs? What role do they play?
There are actually two types of RNNs working in tandem here. One focuses on the history of how each clause was derived. It's like looking at the family tree of the clauses, tracing their lineage back to the original problem.
So it's learning from the prover's past actions, seeing which derivations led to successful proofs before. That's pretty cool. What about the other RNN?
That one focuses on the structure of the clause itself. It's like analyzing a sentence to understand its meaning. It examines how the symbols and subterms within each clause are arranged.
So we've got one network analyzing the history, another analyzing the structure. But wait, there's also mention of these simple features that the network considers. What are those all about?
Think of those as additional clues that the network takes into account. Things like the number of variables in a clause, whether a clause is derived from the original goal, and even those classic age and weight heuristics we talked about earlier.
Ah, so it's not completely abandoning those traditional approaches, just adding a whole layer of intelligence on top. But how do they actually train this network to, make good decisions? Do they just give it a logic textbook and say, go learn?
That's where the magic of reinforcement learning comes in. They basically gave the network a bunch of already solved problems from this huge database called the TPTP library, a goldmine of theorem-proving challenges. It's like letting a student practice with past exam papers.
So the network is learning by example, seeing which clauses were used in successful proofs and trying to figure out what makes them good.
Exactly. It's like watching an expert at work and trying to absorb their techniques.
All right, I think I'm following so far. We've got this sophisticated neural network designed to analyze clauses from multiple angles. But did this whole elaborate scheme actually work? Was the network able to outperform those traditional heuristics?
That's what we'll delve into next. The results are definitely worth exploring. So remember how we talked about the TPTP benchmark being like the ultimate test for any automated theorem prover? Well, this neural network didn't just pass the test, it blew it out of the water.
Okay, spill the beans. How much better did it actually perform compared to those traditional methods?
It wasn't just a slight improvement. We're talking about a significant leap in performance. The network was able to solve problems that had previously stumped even the most sophisticated theorem provers.
Wow, hold on. Are you saying this neural network cracked problems that no other system, no matter how complex, had been able to solve? That's huge.
It is. And here's the kicker. It didn't just solve more problems, it solved them with significantly fewer clauses.
So it's not just about brute force. It's about working smarter, not harder. That's incredibly impressive. But how do they actually make sure this neural network wouldn't, slow down the whole proving process? Adding a whole layer of machine learning seems like it could create a lot of overhead.
You're right, that's a valid concern. Speed is crucial in theorem proving. But the researchers were very clever about how they integrated the network into the prover. They designed it with efficiency in mind.
Okay, I'm all ears. What kind of tricks did they use to keep things running smoothly?
Well, one key insight was that constantly evaluating every single new clause as it popped up would be incredibly inefficient. Imagine trying to read a book while stopping to analyze every single word. You'd never get through it.
Yeah, that would be a nightmare. So what do they do instead?
They created something called a delayed insertion buffer. Think of it like a waiting room for new clauses. Instead of immediately analyzing each new clause, they're held in this buffer until a whole batch accumulates. Then the network processes them all at once.
Ah, so it's like batch processing. Right. Much more efficient than handling things one by one.
Exactly. This allows the network to take advantage of optimized matrix operations, which are lightning fast for processing large amounts of data. Plus, it gives the prover time to tidy things up a bit, simplifying clauses or getting rid of redundant ones before they even reach the network for evaluation.
So it's all about streamlining the process, making sure the network is only focusing on the most promising candidates. I'm seeing a theme here. Working smarter, not harder.
Absolutely. And this efficiency-first approach extends even to how they integrated the network into the prover itself. They used a single queue, ordered by the scores generated by the neural network, to manage the clauses.
Hold on, wouldn't using a single queue limit the diversity of perspectives? I thought we wanted the prover to consider different types of clauses.
That's a good point. But remember, the network itself is already generating a diverse set of scores. Think of it like a ranking system. You might have a single list, but it's based on a variety of factors.
Right, so the diversity is baked into the scores themselves, even though they're ultimately presented as a single, streamlined ranking.
Clever. And even then, they didn't completely abandon the idea exploration. They actually added a touch of randomness to the scores using something called gumble noise.
Gumble noise. That sounds intriguing. What does it do?
It's essentially a way to introduce controlled randomness into the selection process. It prevents the prover from getting stuck in a rut, always picking the same types of clauses.
Ah, so it's like adding a bit of spice to the mix, encouraging the prover to step outside its comfort zone and explore new possibilities.
Exactly. It's a subtle but important detail that highlights the delicate balance they struck between efficiency and exploration. They wanted to make sure the network was making smart, informed decisions, but also open to trying something new.
So we've talked about how they designed this network for speed and efficiency. But the real question is, how did it actually perform when they put it to the test?
Well, they pushed it to its limits with a boost training session, and the results were astounding. We'll delve into that in the next part.
All right, we've heard about this boost training session and its astounding results. Let's dive into that. What exactly did this boost training involve?
They took this neural network and trained it on the entire first-order TPTP library, even the test set, which is typically off-limits during training.
Wait, isn't that like letting a student peek at the answer key before the exam?
Normally, yes. But in this case, they wanted to see just how far this network could go. Could it move beyond simply memorizing solutions and actually develop a deeper understanding of the underlying principles of theorem proving?
So they were testing its ability to generalize, to apply what it learned to completely new problems it had never encountered before. That's a high bar.
It is, and the network rose to the challenge. It managed to solve over 130 problems with a TPTP rating of 1.0, problems that no other system had been able to crack.
No way. Are you telling me this network was solving problems that were considered unsolvable?
Well, unsolvable in this context just means no known system had been able to solve them within the given time limit. But the fact that this network cracked them after being trained on the entire library suggests it was learning something fundamental about the structure of these problems.
It's like it developed its own intuition, its own set of problem-solving strategies. That's amazing.
It truly is. And keep in mind, it achieved these results with a relatively modest instruction limit, meaning it was able to do all of this with limited computational resources,
Mm.
efficient and effective.
I'm starting to think they should rename this network the Terminator
Yeah.
because it's just crushing these theorem-proving challenges. But speaking of comparisons, they also pitted it against some of Vampire's other strategies, right? Vampire being the well-established theorem-proving system this research built upon.
They did. And they even visualized the results with a cactus plot, which shows the cumulative performance of different strategies over time. It really highlights the network's dominance.
Okay, paint us a picture. What did this plot reveal?
It showed how quickly each strategy solved problems as the time limit increased. And what's striking is the huge difference in performance between the neurally guided strategy and even Vampire's most advanced techniques like Avatar.
Wait, Avatar. Wasn't that considered a breakthrough in Vampire's performance when it was first introduced?
It was. But this new neural network is outperforming even that by a significant margin. The researchers even point out that the improvement from the default strategy to the neurally guided one is much greater than the improvement Avatar brought to the table.
So this research isn't just an incremental step forward. It's a major leap, a real game changer in the field of automated theorem proving.
Exactly. And it really underscores the potential of machine learning in this domain.
But this is just one research paper, one piece of a much larger puzzle.
Yeah.
There must be a ton of other exciting developments happening in this field right now.
You're absolutely right. This paper is just a glimpse into what's possible when you combine the power of machine learning with the rigor of theorem proving.
Well, dear listener, we've reached the end of our deep dive into the fascinating world of neural clause selection and automated theorem proving. We hope you've enjoyed this journey into the cutting edge of computer science and mathematics.
If you're eager to learn more, we highly encourage you to check out the research paper itself. It's packed with technical details and thought-provoking insights.
Until next time, keep exploring the frontiers of knowledge and stay curious.